We're all here in the audience in one of these capacities. We've always had the responsibility to understand what we're doing and the consequences of our labor, and to really think very carefully about fairness, accountability, and transparency. Fact. So due to the incredible importance of these topics in data science, we thought it would be really great to have a FATML tutorial for you by Arpita Biswas from Google Research and Uma Sawant from LinkedIn. Go ahead.
Arpita, we can see your screen. Yes.
Yeah, can you hear me as well?
Yes. Uma,
Okay.
Hello, can you hear me?
Yes, yes,
Yes,
we can.
Uma.
Yes.
Great.
Okay, great. So, yeah, thank you everyone for, let me try to minimize this. Okay. Yeah, so thank you for everyone who are attending this tutorial. And today we are going to see what is fair and what is not when we talk about algorithms making decisions for societal problems. For example, when algorithms, we depend on algorithms for deciding who is going to get a loan or not, or who is going to get hired for a job or selected for a job interview. So algorithms play a major role in such decisions, and we are going to see that how can you audit for fairness or bias in such decisions. So I am Arpita. I am a visiting researcher at Google Research, and also I recently completed my PhD at Indian Institute of Science. And with me I have Uma Sawant. She is an engineering manager at LinkedIn Bangalore. So as we know that this fairness in algorithms in general is like a very huge topic, and it is getting a lot of attention in the recent like 5 to 10 years. So just to limit the scope of this tutorial, we will only talk about fairness in classification and fairness in ranking algorithms. And we also have a small demo to show using the what if tool, again created by Google Research, just to give you a flavor of what kind of fairness we are looking at. So, okay, let's start with what is a classification problem. So what we have is a set of labeled observations that we start with. It's also known as the data. And then typically we would like to split this data into training and test set. And then we have a machine learner, or let's say an algorithm. If you are familiar, this algorithm can be logistic regression or SVM or any other algorithm, deep networks. So you use that algorithm to finally build a prediction model. And once you have this model, typically you would use the test data, which is unknown, which the machine learner has not seen yet. And we would like to get some statistics around how good the prediction model is. Now, typically, let's say we are here talking about like a binary classification problem. So whether a loan needs to be approved or not, whether this person will be hired or selected for interview or not, this kind of questions this prediction model would answer. So given a new data, which is basically the features of a particular individual, the prediction model is supposed to give a positive label or a negative label. Positive meaning that yes, your loan is approved. Negative meaning no, it's not approved. Now, to assess the performance of this prediction model, we use these terms like accuracy, specificity, F1 score, etc. But what about fairness of this prediction model? How can we say that this prediction model is fair across two different genders? So if you look at male and men and women, then this prediction model acts in a fair way. So, so today mainly we'll try to discuss this different kind of fairness notions which are there in the literature. And basically the key questions in this entire fairness space is, how do you even define what is fair? Second, once you define a fairness notion, can you ensure that your algorithm act in a fair way? And then can you show the trade-off with accuracy? Can you show that if you have like a really fair algorithm, it might hurt the accuracy? So can you like then balance it with accuracy and make a better decision in some sense. So let's first look at what are the different kind of fairness notions which are there in the literature. So there are three main categories of fairness. One is known as individual fairness, which talks about an individual's satisfiability with respect to the answer or the prediction that individual would have got. The second is group fairness, which means that you divide the entire population into some groups. And let's say for gender, you have male and female. These are two groups. Now, the fairness notions are defined around how equal are the predictions in these two groups. And I'll talk more about more specific about some of the group fairness notions in this talk. And then the third is counterfactual fairness, which says that if instead of being a male, this person was a female, would the prediction would have been different. So this is known as counterfactual fairness, when an algorithm says that okay, it's not that if you just keep everything intact and just change male to female, your answer is would change, the answer of the prediction model would change. So if this doesn't happen, then that's counterfactually fair. So let's first look at what is individual fairness. So here the idea is that similar individuals should have similar predictions. So if you take two individuals who are very similar in the education they have received, the kind of job they do, the kind of salary they get, and yeah, if it is almost similar in most of the features, then their predictions should also be similar. So if one of them gets a loan approval, then the other should also get a loan approval. Should not be different. So the positive thing about this notion is that it imposes a fair treatment between every pair of individuals. The negative is that the similarity matrix is a difficult choice. So how can you even say that these two person are similar? What features do you take? Do you say similar if they are from the same gender, or do you say similar if they are having other characteristics as similar? So similarity matrix is itself a big question, and people have been like dealing with this problem in individual fairness for even it's open now. So a more popular fairness notion is this group fairness notion. And so I'll talk about a few group fairness notions in the next few slides. So let's start with no disparate treatment notion of fairness. So this says that a sensitive attribute which is sensitive, for example, gender, if it is a sensitive attribute, if you don't want your classifier to be biased based on male or female, then don't give this attribute to the model in the training set itself. Just remove it from the training data. So that is what no disparate treatment would be. The good thing is, again, it's legally motivated. You might have like a legal term that you cannot use gender as a deciding factor, so it's fine to just remove it. The problem is there can be other features in your data sets which are highly correlated with this sensitive attribute. Maybe with female there are other features which are directly correlated, and then even if you remove this feature called gender, then other attribute is somehow making the entire algorithm biased against female. So there are many papers that talks about this particular problem. It's also known as redlining problem. And they have shown that it is not a very good idea to simply blindly remove the sensitive attribute from the training data. So the next best thing to do is to impose extra constraints. So you can try to maximize accuracy, but then you can input some extra constraints with the optimization problem. And one of them is known as demographic parity. It says that the ratio of the fraction of positive outcomes of one group should be equal to the other group, which means that if you look at Z, so this is a particular attribute, and let's say Z equal to 1 is female, the group female, and Z equal to 0 represents the male group. So if the prediction, so the fraction of people who gets a positive prediction should be equal among both male and female. That is, let's say among all the male applicants, if 60% of them gets loan approval, so among all the female applicants also there should be around 60% of female applicants who should get a loan approval. Again, the advantage of this notion is it foresees the possibility of discrimination that would have happened in the training set. So it tries to remove those kind of disparities. The problem with this notion is it may not be compatible with a perfect classifier. So perfect classifier is the one which gives 100% accuracy. So you might have a classifier that gives 100% accuracy, and then it may not satisfy this equality criterion. So it will be called unfair. So that's one problem. And the second problem is that it's a non-convex constraint. So if you're familiar with NP hardness of problems, then basically this entire problem is very hard to solve, and it will take a lot of computational power to maximize accuracy subject to this particular constraint. Another popular group fairness notion is equality of opportunity. So here we are talking about equalizing the true positive rates. So if you look at this two expression, here we have an extra term in y equal to 1. So we are looking at all the female who has a positive label with them. So here we are talking about the ground truth. Let's say you know that given a loan, this person would have repaid the loan, and then if you have that if you have those labels at hand, then you want to assess that how good the classifier has done with respect to this particular group of female who would have repaid their loan. How many of them are actually given predicted like having a high score by the prediction model itself. And same, you can look at male who have repaid the loan and see the fraction of people among them whom the prediction model have predicted positive. And you want this true positive. So this is called true positive rate. So you want this true positive rates to be equal in two different groups. Good thing is it's compatible with perfect classifier. So if you have a classifier which is 100% accurate, then which means basically y hat, which is the prediction, that is going to be exactly equal to y, which is the ground truth. That's a perfect classifier. So this term will always be like 1 and 1 on both sides. So it is actually compatible with perfect classifier. The problem with this is it is a non-convex constraint problem. So again, like the earlier group fairness notion, this is hard to solve. So there are many others, but if you are more interested in this fair classification domain, we can look at some of my papers, and I'll quickly move to a demo where can I, let's see. So is my screen visible?
Yes.
Okay, great. So let's look at this particular. So this is called what if tool, and
Wait,
you can actually.
Arpita, we can't really
Okay,
see the what if tool demo. So
you can't.
it's still on the slide. Yes.
Oh, okay, but I shared the screen. So let me. Should I?
Maybe close out the deck.
Yeah, I did that. Can you see it now?
Not yet.
Let me see.
Uh,
Shows.
I'm changing you from the presenter, and I'll give you the presenter right again. Then try.
Can you see
Yeah.
it now?
So, yeah.
Um.
Uh, can you try now?
Okay. So can you give me the presenter?
Yes, I've given you.
Can you do it again? I don't see that anymore.
Um,
Okay, now I got it.
Based on what?
So can you see it now?
I actually can't.
Let me. Is it visible now? No.
Not yet. No.
So I have.
You can go to sharing. You can show, and under the show option, you can see other options. Just open
Yes,
share.
yes, I just did that.
Yeah.
I can you see it now? How does it?
It's not. It's not there yet.
Okay. Okay, maybe is. Hi, Geeta.
Hi, Geeta.
Okay, maybe then Uma can continue with the next part, and in the meantime, I'll see what to do.
Sure, Arpita. Thank you. You're still a presenter, so you can try. Thanks. Hi, Uma.
Sure. Hello, can you hear me?
Yes, we all can hear you. You can take the stage
Great.
now.
Yes, thank you. Can somebody please share the slides?
Ankita, can you go ahead and share the deck?
Give me a minute.
My apologies to the audience. My video is not working due to a browser issue.
That's all right, Uma.
Okay, so far Arpita talked about the very important problem of fairness in classification. I'm going to talk about a parallel problem, that is fairness in ranking. So we see ranking problems all the time in web. So for example, you have search engines and you see a ranking of results, right? Similarly at LinkedIn, we also work on multiple ranking problems. So I'll just keep talking till the slides appear. Right, so I'll set the stage. What kind of ranking problems do we work on? So at LinkedIn, the mission is creating economic opportunities for every member of the workforce, right? So one way to do this is to enable people who are recruiting to reach people who want to get recruited. So for this purpose, we have a search engine which allows recruiters to search by, let's say, a title, right? So let's say a person is hiring for a software engineer role or a manager role. Or you could also search by skills. Let's say I want to hire a person for Java skills or maybe front-end developer skills and so on, right? So it is important both from ethical point of view as well as LinkedIn's point of view that we maintain fairness while we present the results, right? So we do not. So how do we ensure that our ranking algorithms are indeed fair? Is the problem we are trying to tackle here. So that's the objective statement. Let's see if the slides are back. Yes. Can you please move forward? Forward. Down, 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 down. Yes, thank you. So this is the slide I was talking about. So the objective is how do we maintain fairness in talent search? So on left hand side, you see a screenshot of the tool I was talking about. On top hand bar, you could actually type some skill such as data mining or some title, and you would get a result, a carousel of members who qualify for that. Right? So this is one point that this is not my work. I'm representing the work of my colleagues, that is Krishnaram Kantapadi and Sahin Gate. And at the end, you will find multiple references detailing the original work. Right. So can we please move forward? Next slide, please. Yeah. All right. So our objective is to ensure representativeness. So how do we measure? How do we? What is the intuition? How it can be implemented? So ideally, given a distribution for gender or age or any protected attributes in the qualified candidate set, we want to maintain the same proportion in the top rank result. So that's the intuition behind fairness in ranking. You have a qualified set and you have a set of top ranked results, which is what the person searching for will see. And there should be equal distribution in both. Next slide, please. Now, how do we, so this is one way of doing things, that is, given a qualified set, you would maintain the same proportion of attribute values in the result final ranking set, the top rank set. But there is other way you could achieve the target proportion. Let's say as a legal mandate, there may be a legal mandate that there should be equal representation of, let's say, male versus female in the top 10 results. Or a company could make a voluntary commitment that I would reserve at least 10% top ranked slots for a particular gender or for a particular age. So you could decide what the target proportion should be. At LinkedIn, as I said, we take the fairness criteria as the qualified set should have the same representation as the top ranking set. So I hope the problem statement or the goal is clear to everyone at this point. So to move to the next slide. Right. So how do we achieve this kind of this requirement? The main takeaway here is that this is achieved via a re-ranking algorithm. So how do we do this? There is we already have the set of potential candidates. We partition the set of potential candidates into different buckets. What could be those buckets? Those could be for each protected attribute, such as it could be gender bucket, it could be age bucket, up to whatever is the mandate given by the company, right? So once you partition the set, you rank the candidates in each bucket as per your usual ML algorithm. And then the fairness requirement is that you would take the top rank results from each bucket and merge them into a ranked list while balancing the fairness requirements. So that at high level is the algorithm. Now, if you go, if we move to the next slide, I think there is a diagram. Yes. So this block diagram explains what we how we achieve this. So exactly as I mentioned, so on the right hand side there are different indices. Since the entire set of ranked results, entire set of candidate results may not stay in one index. There could be multiple partitions, multiple shards. In each of those, you from each of those you retrieve a set of top K candidates based on the query. Now, our algorithm in particular is divided into two levels of ranking. Just so that, so this is a typically followed method in any of the large scale web ranking mechanisms, that you have a first layer ranking which allows you to do fast ranking on a large, fast and simple ranking on a large set of results, followed by a more complex ranking on a smaller set of results. Now, at LinkedIn also we follow the same kind of procedure, and in each level of ranking we have the representative re-ranker, which is doing the bucketing of results and taking the top results while balancing the fairness requirements. So that at a very high level is the algorithm for fairness in ranking requirements. And how do we perform? So to go to the next slide, this algorithm was tested in LinkedIn, the talent tool, alive. And in A/B test, it was found that over 95% of searches were now representative compared to the qualified search population. So, and it was also seen that this did not affect the business metrics. So, while maintaining the neutrality of business metrics, we achieved a major gain in fairness. So, with this algorithm is now ramped to 100% of LinkedIn recruiters users worldwide. So that was the fairness in ranking, a quick user case. On the next slide, you will see a lot of references of this work. There is a KDD paper, and there are also a LinkedIn engineering blog explaining details. So with that, I'll now hand it back to Arpita. If the demo is ready, we can go through it.
Yeah, thanks, Uma. If you can share the present, yeah, if you allow me to present, then check. Show my screen.
Yeah, I made you the present. Just try once.
Okay. Yeah, I'm just. Can you see my screen?
I can see blank. The reason why it's blank because you might be having other things in your browser, which you all have to close, I guess.
Oh,
that's
okay.
this point.
So, can you now see the browser?
No, we can't.
Okay. Let me try one more thing. So I'm getting an option of screen and screen clean. I just clicked on screen. Is it visible? Wait.
No,
Now?
not yet.
Okay, I'll just try a few more things. So now I've clicked the entire screen, but it's still not showing. So can you see just a blank screen? What can you see exactly?
So it's showing a black screen at this point.
Black screen, is it?
Yeah. And even your video is not visible.
Yeah, I just switched off the video, so I thought I'll just first check if there's a network issue, but I don't think it's a network.
No.
So
So please switch the camera back if possible, and if
yeah,
you want, mute the session.
yeah,
That would, yeah.
sure. Okay. Oops. So somehow I'm not seeing the sharing option anymore. Can you make me a presenter again?
Yes. Done.
Okay, I didn't get anything. Sorry for this. I don't know what's yeah. Okay, I just got it. When ready, show my screen.
I can see your screen now.
And the demo?
Demo.
Is it in
I
the
can
demo page?
see the desktop.
See the desktop. Okay.
The wallpaper.
Oops. Why? So I'm sharing my entire screen. Now I'm sharing just this browser. And
Arpita, try moving the browser towards right or left, like out of your own screen.
I think the key is to hit share screen after you're ready with the what if tool open. And then hit
yeah, so the what if tool is open.
And then hit share screen once you're on it.
Okay, I did that actually. Yeah, I just clicked on the what if tool window for sharing option, and it's showing me that you are sharing. Yeah, sorry, something is wrong with. I don't know if it's a software issue because it generally works with other like.
We can try one more thing here, that I will be able to give you the Google Hangouts link where you can share your screen with me there, and I can share your screen with the audience. Does that
Sure.
work?
Sure. Yes, yes, that works.
So I'm giving you a link. Please join that
Mm-hmm.
link.
Yeah, sure.
Hi guys, how do we go to the actual place where it's getting presented? Attendees, is it?
Sorry?
So I'm Geeta here. So now
Hi.
next is
The panel discussion, yes.
next is panel discussion, is it? So okay. So when going? Arpita, you're next. Are you next
Sorry.
panel?
No, I think our session is till 4:05. So I'm still stuck in trying to present the demo, and I think we're trying to find an alternate way to present it.
Okay, so please join the link I shared with you over WhatsApp.
Oh, okay. I have to open WhatsApp on my desktop, so just give me a minute. Sorry for all this.
No problem. We are really sorry, all the attendees. Just give us 2 minutes and I'll make sure that we are trying our best to make it happen. As you know that digital applications always has some of the glitches here and there. And thank you for your patience. Meanwhile, you can put your questions on the question bar. As I've shared the question bar here in a chat box. And I would be very, very happy to take your questions and we'll definitely answer all of them. So yeah, so Aruna, please, Arpita, please try to share your screen here.
Yes, I'll do that.
Yes, we can see.
Okay, I'll just mute the Google Meet thing. Okay.
So everyone can see it, right? I can see it.
Yes,
Yes,
So yeah,
Ankita, it's fine.
you can see.
Okay,
thank
great.
you.
So
Sorry,
yeah,
yeah, with this. So please, yes, go ahead.
yeah. So this is so this demo is about a classification problem that tries to predict the salary of an individual, whether the salary of that individual is greater than $50,000 per annum or less than that. So this is a pre-built model, and I'm using what if tool to show you the demo, and you can play around with your own model, and this is available in TensorFlow and Jupyter Notebook. So feel free to download it and plug in your own data set, own algorithm. So the way it happens is it's classifying. So the blue ones are the people who were given like a negative label, which is basically they get like less than equal to $50,000 per annum, and the red ones are the higher scored ones. So the features that it use this particular data set has are age, capital gain, and number of hours they usually work, their capital loss, education, etc. So let me quickly go to the fairness aspect to, I'll just do it very quick because I'm running out of time. So if you just run a plain algorithm, so here they have just trained a logistic regression. It shows that the total number of predicted positives, which is the fraction of people to whom it would predict as positive, that's only 18.4%. However, if we slice it by gender, then yeah, if we slice it by gender, now you can see the output grouped into male and female. So among male, the predicted yes percentage is 23.3, and among female, the predicted percentage is around 8.1. So you already see that the fraction of predicted yes among two different groups looks very different. Now, if you remember that a few slides back, I was talking about something called demographic parity, which wants to ensure that the predicted yes are equal in two groups. So let me click on demographic parity, and it would just plug in this extra constraint in the optimization function, and it will recompute the entire classifier, and you have a different classifier now. So after plugging in demographic parity constraint, now you see that the total number of predicted yes is 10.3%, and among male, and among female it is 9.9%, which is close enough. Previously it was like the disparity was really high. So you can also play around with other fairness notions and see what happens. I'll quickly show you one more thing about the context, the counterfactual fairness. And yeah, so here, so counterfactual fairness would say that you pick a particular point. Let's say I pick this, but reference score 1. Just a minute. Yes, so let me pick this point and see. So this is a female, this is a male, and okay, just a minute. So this algorithms typically take some time to train. So whenever you're using the tool, you'll see that there's some time lag between the training phase and what you see. So here, let me pick a particular data point. Let's say this is the data point, and you can see all the features of this data point, and it has been predicted as positive, greater than 50K. And let me change this label to female, and let me re-predict this particular data point. You see that from prediction of red, it has gone to a prediction of blue. So just by changing this one feature, everything remaining intact, changing it from male to female has changed the entire prediction. And again, if I change it back to male, then you'll see it will again predict it as red. So this is called counterfactual fairness, and this platform again gives you a way to see that such counterfactual unfairness is happening in your prediction model or not. So yes, sorry, I plan to show some other things, but I think I'm running out of time. So you can use this particular tool to assess the fairness of the algorithm that you have trained. So this brings to the end of my demo.
Thanks, Arpita. Thanks so much. Thanks, Uma. I know the tool gave a little bit of a trouble, but I think we got over that as well. So thank you for that wonderful tutorial. So moving on, we all have a clear understanding of the value of data and how we use it in decision making through actionable insights. As of today, though, the estimate is that only 13% of the AI models actually make it to production. So next we have